Now, before we get too deep into atmospheric chemistry, we need to pause and actually jump to the appendix in the book to do a little bit of review on oxidation numbers, or also known as oxidation states. And the reason for that is that there's this term or set of terms that you'll come across often in the textbook where we talk about species being partially oxidized. We talk about conditions being oxidizing or reducing. But what do we mean by partially oxidized or oxidizing? What does that mean? That brings us back to this discussion or review of oxidation numbers and states. So there are some rules for oxidation numbers, and they are listed in order of precedence. So rule number 1 takes precedence over anything beneath it. Rule number 2 takes precedence over rule number 3, etc. If there's ever any conflict. So first, the very first rule is that the sum of all oxidation numbers in a substance must equal the net charge. And it's important to point out that every single element, every single atom in a compound has an oxidation number or oxidation state. And it helps us keep track of redox chemistry. Changing oxidation numbers involves gain or loss of electrons. So back here again, so the first rule is that the sum of all the oxidation numbers in a substance must equal the net charge. So if it's a neutral compound, they all have to add to 0. If it's an ion, they have to add to the ion charge. The second rule is that for unbonded atoms, the oxidation number equals the charge on the atom. So if we're talking about ions, then in this case, like potassium ion, K+, then the oxidation number for potassium here would be +1. Whereas if we're just talking about a neutral oxygen atom, then its oxidation number is 0. Iron 3+, its oxidation number would be +3, or the O2- anion, it was the oxidation number for oxygen here would be -2. The third rule is that fluorine is always -1, that group 1 metals are +1, and group 2 metals are +2, and aluminum is +3. So remember, group 1 is the lithium, sodium, and potassium. Those oxidation numbers, whenever they're in a compound, is +1. Group 2 would be things like calcium and magnesium. Those we already know normally take a +2 charge in ionic compounds. Here they have a +2 oxidation state, and aluminum normally takes a +3. The next rule is that hydrogen is always +1 unless it's bonded to a metal, in which case it's -1. Rule number 5 is that oxygen is always -2. And rule number 6 is that chlorine, bromine, and iodine, so the remaining halogens other than fluorine, which is addressed in rule number 3, are -1. Now, we've got 6 rules, but remember that they are listed in order of precedence. So sometimes rules higher in the chart will need to take precedence over rules lower in the chart. And let's go through a few examples of that. So first example here is HF, just very simple. We've got hydrogen and fluorine. If I look at my rules, I can say, well, first off, the sum of the charges, or the sum of the oxidation numbers, must equal 0, according to rule number 1, because this is a neutral compound. So whatever the oxidation number for hydrogen and the oxidation for fluorine is, the number must add to 0. And that turns out to work just fine, because we're following rule number 3, fluorine is -1, and following rule number 4, hydrogen is +1. So everything's all balanced. We're perfect. It gets a little bit more complicated. Let's take a case where we were talking about hydrogen peroxide. So according to rule number 1, the sum must equal 0 still, and that's one always takes precedence. And then we kind of work our way down, and rule number 4 comes in, and we get hydrogen's +1, so rule number 4. But if I follow rule number 5 and say that oxygen is -2, then I would be breaking rule number 1 because I have 2 oxygens. Each of them have an oxidation state of -2. Then I would have -4. Hydrogen's only +1, that would be only +2, and I would end up with a -2 charge, which is not correct. So rule number 5 is outranked by rules number 4 and number 1. And so rather than being -2, oxygen can only be -1 in this case. So oxygen takes a -1 charge, or it's not a charge, it's an oxidation number. Oxygen's oxidation number or oxidation state is -1 in this compound. And we can sort of write this out in an equation where we can say if the sum of all the oxidation numbers must equal the overall charge, I can write, well, 2 times the oxidation number of hydrogen plus 2 times the oxidation number of oxygen must equal 0. Hydrogen is +1. Oxygen, then, if I do some algebra, comes out to be -1. A third compound here, this is an ion now, so ClO2-. If I look at this and say, well, according to rule number 1, the sum must equal -1. Oxygen then is -2 according to rule number 5, but chlorine can't be -1 because if it was, we would end up with a, rather than ending up with a -1 charge, we would end up with a -3 charge. Actually, no, sorry, a -5 charge, because oxygen is -2, there's 2 of them, that would be -4. If chlorine was -1, that would be -5. But the overall charge on the compound is only -1. So I simply take the equation and say, well, chlorine plus 2 times whatever oxygen is must equal -1. Oxygen is -2, and so chlorine must come out to be +3. And that's essentially how we would go through and use these rules to determine the oxidation number for any element in any compound or ion. But let's carry it a little bit forward, or a little bit farther. Let's say, so what exactly do we mean by oxidizing conditions? Well, now let's look at reactions. Let's take this reaction here where we have methane reacting with oxygen to form CO2 and water. If I go in and list the oxidation numbers for each element in each compound, I can say, well, in CH4, I don't know anything about, carbon doesn't come into my rules, but hydrogen does, and hydrogen bonded to a nonmetal is +1. And rule number 1, the sum must be 0, so carbon must be -4 as its oxidation state. And then oxygen is in its elemental form, its overall charge is 0, so it must be 0. Its oxidation number must be 0 in this case. On the product side, however, I've gone to a case where CO2, now oxygen is -2, according to rule number 5, and carbon must therefore be +4 in order to satisfy rule number 1. And hydrogen is still +1, oxygen is -2, so that works out fine in water. What we notice if we look at the change in oxidation states is that carbon went from -4 to +4, which means that it must have lost electrons. It goes from a minus charge all the way up to a plus charge in terms of its oxidation number. So it got oxidized. Oxygen, however, went from 0 to -2, so it got reduced. And so if I think about what does oxidizing or oxidation mean, well, oxidation is raising the oxidation number of an element, and vice versa for reduction. So reduction is lowering the oxidation number for an element. And this occurs by the gain or loss of electrons. Remember the kind of memory device oil rig? Oxidation is loss of electrons. Reduction is gain of electrons by that individual element. And so if I track the oxidation number of an element through a reaction, I can determine whether it was oxidized or reduced. Now, there's another helpful tool that we can remember when we're talking specifically about atmospheric chemistry, although it's not limited to atmospheric chemistry, but it turns out that oxidation frequently involves adding more oxygens to an element. May even be where the term oxidation came from. But oxidation does involve, or frequently, not exclusively, but frequently involves adding more oxygens to an element. So if I show here just an example, going from carbon monoxide to carbon dioxide, the oxidation state of carbon goes from +2 to +4. And so you can see that we've oxidized carbon in this case. And reduction frequently involves adding hydrogens to an element or removing oxygens. Either one of those is a frequent occurrence when we're talking about reduction for an element. So an example here would be taking CO2 and converting that to the formate ion. So I simply added one hydrogen to this. It's an ion now, and we'll notice that I went from +4 down to +2. And so we've undergone reduction in that case. So a simple memory device here for remembering oxidation or reduction, in addition to the gain or loss of electrons and the raising or lowering of the oxidation state, is frequently that adding oxygen or removing hydrogen is oxidation. Adding hydrogen or removing oxygen is reduction. So if I'm talking about oxidizing conditions, what I'm talking about is an atmosphere where where if a molecule came in that you could add oxygens to or raise its oxidation state, that the atmosphere is primed to do that, to remove hydrogens and add oxygens to a compound. So our normal atmosphere containing a lot of oxygen is generally termed kind of an oxidizing atmosphere. Now there's another kind of little bit of descriptor here that would be helpful. Sometimes we talk about elements or compounds being fully oxidized or fully reduced. What does that mean exactly? Well, let's just look at a few examples. So the fully reduced form of carbon is the one where we've added as many hydrogens to it as we can. We've got no more, and we've got no oxygen. So adding essentially the fully reduced form of any element is the one that has the most number of oxygens that it's able to have. Carbon can have 4, and its oxidation number, you'll notice, is the most negative that it can be, -4 for carbon. Nitrogen, the most that you can add to nitrogen is 3. Now you could form the ammonium ion, but it won't cause the oxidation number to be any lower. So in this case, nitrogen can have an oxidation number of -3. Sulfur can be -2. Phosphorus can be -3, and oxygen itself can be -2, and it normally is -2. And then we can look at, those are the fully oxidized, the ones where we have the most number of hydrogens attached. The opposite is basically when we have the most number of oxygens attached to an element. So for carbon, that ends up being CO2. Now, even if we looked at a case where if you took carbon and added 4 oxygens to it, and then made I guess all of these would have to be minus charges since nothing else is attached to them, we would still only end up here with a +4 for carbon in this particular case. But that's not a normal compound that we see. It's not a stable compound at all. So CO2 is generally the one that has the most oxygens that we can add to it. I guess we can also, since many of the other examples I've listed are ions, perhaps it would be helpful to talk about the carbonate ion, which we can see here, carbonate ion. If I look at this and note that I have to add up to 0, I can say, well, carbon, whatever carbon happens to be, +3 times oxygen, it's got to equal -2. Well, oxygen is normally -2 itself, so -2. So it would end up being, plus there, carbon, -6 is equal to -2. So carbon would just end up equaling +4 again. So in both cases, Carbon's greatest oxidation number is +4. And for the nitrate ion, it's about the most oxygens we can add to nitrogen. It ends up at being +5 for nitrogen. Sulfate can go all the way up to +6. The phosphate ion is +5. And then we have, in this case, O2 is the common most oxidized form of oxygen, which is just 0. Now, technically, there is one other more oxidized form of oxygen, but it's very rare, and it only involves cases where we have oxygen and fluorine compounds. So OF2, for example, because fluorine, the rule about fluorine comes above the rule about oxygens, fluorine takes precedence, and fluorine is -1. There's 2 of them, so oxygen must be +2 in this compound. Those are really extraordinarily rare exceptions, really only involving fluorine, where oxygen would then have an oxidation number greater than 0. So in most cases, we will ignore that exception. So these are the fully reduced and fully oxidized forms of the elements. That's what we mean. Maybe another example or examples of partially reduced elements will be helpful. So partially reduced or oxidized species simply lie somewhere in between. So for example, formaldehyde here, we can calculate this. Each hydrogen is +1, oxygen is -2, so carbon actually ends up having an oxidation number of 0 in this case. So it's in between its range of -4 to +4. And one thing I sort of failed to point out in the table up above is you'll notice that the range for most of these is a range of 8, all the way from -4 to +4, or from -3 to +5, or from -2 to +6. There's generally a range of 8 between the fully reduced and fully oxidized forms of an element, with the exception, of course, here of oxygen that has a normal range of about 2. SO2, in this case, so this is sulfur dioxide, a common atmospheric gas. Sulfur here is actually only partially oxidized because its oxidation number is +4. Fully oxidized would be all the way up to something like the sulfate ion. Nitric oxide, again, another common atmospheric gas. Here, nitrogen's only at a +2 oxidation state rather than the fully oxidized +5. And even something like hydroxyl radical, which is just HO, just neutral HO. In this case, the rule about hydrogen comes before the rule about oxygen. So oxygen itself is only -1 oxidation state in this case. So oxygen is only partially oxidized in this case. So this is a little bit of information about how we do oxidation numbers or oxidation states, and what we mean when we talk about fully oxidized or fully reduced or oxidizing or reducing conditions. Since this will come up primarily, I think, in chapter 3, but you probably see it here in chapters 1 and 2 as well.